Okay, so as always, we start by looking at the website because I want you to remember that it's there with all your instructions. Even at this late date, there are people who tend to forget such things. Today is the 16th. This is the last class for this week. We are discussing binary trees. Friday is Good Friday and the university is closed. We will discuss binary trees one more class, and then we're on to another topic. A week from Friday, we will have our last regular lab. So it's getting down to the wire. Any questions? All right, let's go back here and scroll up here and go to my slides. Now, these slides really are sort of a thin layer on looking at code, as is usual here. So what is a binary tree? It's a data structure with a left and a right child. So we have a picture of it to the right there that I copied from somewhere. And what it's going to do is it's going to keep each node is going to have a left and a right branch to it. Like, remember, a linked list had a next? Well, this is going to have a left and a right instead of a next. And then each node is also going to hold a data item. In this case, it's holding integers. And it's always going to keep them in sorted order. And so the way it's going to work is if I'm at the root, everything to the left is going to be less than me. And everything to the right is going to be greater. So that holds for each step down the tree. Make sense so far? All right. We call the tree balanced if the height of left and right nodes differ by 1. So the height of this tree is 3, right? We have 1, 2, 3 levels, right? If we say, like, if this one only had that, we could still say it was balanced because it only differs by 1, right? So if it only differs by 1, we're going to say it's balanced. If the height is only difference by 1. And most operations on balanced trees are going to be order log n, because in order to find a node, for example, you're going to have log n traversals to get all the way to the bottom leaves of the tree. Any questions about that? Okay, so far, nobody's lost. And if they are, they're afraid to tell me, which is a bad thing to be at this stage of the game. Okay. So properties, the left child is always smaller, the right child is always bigger. It follows that everything in the left subtree is smaller and bigger, which is what I just said. And we can visualize B trees. I used this is a tree that was generated by a code that I have. It just sort of shows you a picture. I sorted a sentence, all the letters in a sentence. And this was, the quick brown fox jumps over the lazy dog. So it has all the letters of the alphabet. And this one is not balanced, right? You can see lots of places where it's not balanced, like this. This is not balanced, right? This has got 2. This has got 3 down, and this has got 1. So, but you get it's not horribly badly balanced, right? This is just sort of randomly. Yes, Scott.
The right side K is more left.
Yeah, so this is sorting from left to right. So J is less than K, K is less than O, and M, L, P, right?
Say the left side always be larger side.
No, it was smaller. So left child was always smaller.
Okay.
And then the picture was left side was smaller. No, smaller means the values in the nodes are smaller.
Okay.
The height, we want the height to be, for a balanced tree, we want the height on each side to differ by at most 1, but the height can differ by more than that. It can be bigger on the left or right. It doesn't, depending on how things shuffle. That's not the important thing. the important thing is that everything is kept in sorted order. So I told you before, the tree map, yes, what's your name?
Very top.
I'm sorry, I couldn't hear you.
Luis, very top.
I don't know. It's a T, I guess. I saw it briefly before it flashed down. Yeah, that's looks to be a T. You can look at the slides online and you can see. I'm sorry about the way that Zoom obscures things, but it's life. Yes. Oh.
What's the point of?
Yes, if it's balanced. So I told you that most operations are log n if it's balanced, right? So imagine a tree which everything only has a left node and it goes all the way down this way, just, all the letters in this order, right? Now, that's to look things up in a tree like that is order n, right? That is not any better than a linked list. So the idea behind a tree is it's only really helpful if it's balanced. Okay. So now we get to look at code. Yay. Okay, so I have like a base node class trying to, you try to factor out the code in a way that's simple to look at. And sometimes you get the abstraction right and sometimes you don't. So in this class, so what I chose to do here is create an abstract class, which means that some methods are filled in and some methods aren't. And so I have a left and a right base node. I have a character C, which is the data. I'm keeping a character on this one. I always used an int before, but for binary trees, I like to use a character by default. And a character, as you may recall, is kind of int. It's an unsigned int with 2 bytes. Anyway, so I have an abstract method add and toString, and I have a method for determining the height of the tree. Now, the method for determining the height of the tree is recursive. So what I'm going to do is I'm going to create 2 integer variables, height right and height left, and initialize them to 0. And if the right tree is not null, then I'm going to update HR with right.height. And if the left is not null, then I'm going to update the left. And then if the right side has a greater height, I'm going to return 1 plus the right side. Otherwise, I'm going to return 1 plus the left side. Now, the 1 plus is for the current node. Okay, so it's I'm asking my right child, how high are you? And then I'm going to add 1 to that for myself and pass that answer back. So that's the way the recursion works. Does that make sense to everyone? Does somebody have a question? So everything we do with a binary tree is going to be recursive. That's the essence of the data structure. Okay. Node count. So different from height is the node count, right? So we expect the height in a balanced binary tree, the height should be the log of the node count, right? Log to the base 2 of the node count, roughly. So the node count, I'm going to say the node, it's going to look very similar, right? These first 3 lines look the same essentially as these, right? I'm doing the same kind of thing, except, node count is calling node count. What differs is what I do with the result. So when I want to count the nodes, I say 1 plus the nodes on the right plus the nodes on the left. 1, again, I'm counting myself. So so you can see the difference here. One is sort of getting a maximum and the other is doing a sum. Okay, are we good? If I asked you a quiz on this and left blanks in here, you'd all get it, right? Yes, Chris. What's that? Yeah, so what we're doing at height, right, is we're taking the maximum of the, we want to find how high the tree is, right? And so we need to find whether our right side is higher or our left side. And And finding the height is like finding a maximum of that. So I want to take the maximum and add 1 for myself and return it. And if I do that recursively, I will pick out the correct height. Anybody have a question? Yes.
What is the 1 plus? I know HR and HL is like the left and right height.
Yes.
What does 1 mean? Why do we need to?
Because it's the current node, right? It's 1 is for the current node. So if I call each time I go down that tree, right, I'm adding 1 for the current node. It's counting the height, but it's only counting it if it's adding to the height, right? So if let's go back. All right, if I am looking at this tree, right, and I'm starting at the letter C, and I want to know the height, right? I'm going to ask for the height of B, and B is going to ask for its left child, and its left child, the height is going to report as 0, right? So B is going to say, well, my height is 1 because I have a child that has a height of 0. And C is going to say, I have a height of 2 because I have a child that has a height of 1. It's going to look at the 2 sides, right? This side has 2, this side has 1, so it's going to say 3.
It's counting. Just really like 2 sub-branches.
Yeah, it's counting on each side. It's taking the bigger 1 and adding 1. All right. All right, visit. So visit is a cool thing that you can do if you've got a data structure that's tree-like. Well, you can do it with almost anything. But the idea is I have a thing called a binary tree visitor, right? And what I'm going to do is if the left side is not null, I'm going to visit the left. When I'm done doing that, I'm going to visit the current node. And then if the right is not null, I'm going to visit the right node. So what that's going to do is it's going to visit all the nodes in order. And what is this binary tree visitor? It's just that, right? It's an interface with a single method called visit, and it takes an argument of base node. And what you can do is you can implement this class, and you can pass this to the tree, and your method will get called with every node of the tree. So it's kind of like an iterator, if you want to think of it that way. Make sense? It's a useful thing if you want to do some kind of tree-wide operation. Okay. Contains. So here I want to find out if a piece of data is contained in the tree. So what I'm going to do is, first thing I'm going to do is I'm going to check to see if this dot C is equal to C. And if so, I'm going to return true. If C is less than this dot C and the left is not null and the left contains C, then I'm going to return true. If this dot C is less than C, which is the opposite condition here, and the right is not null, and the right contains C is true, then I'm going to return true. And if all 3 of these tests fail, I'm going to return false. So this again is a recursive method, right? It's saying if my node has the value, then we're done. If my node is less, I'm going to pass it to the left. If the value you're looking for is greater, I'm going to pass it to the right and give you the answer. Make sense? Are you raising your hand? No. Okay. All right. So that's the base node class, right? That's just sort of the foundation for everything. And now let's look at our first binary tree. So my binary tree is going to implement iterable, not surprising. And it's going to have a public class node that's going to extend base node, and this dot C equals C. And I'm going to have an add method. So that's one of the things I left as abstract, right? So on my base node, my add method is going to take a character, and if the character is to the right, right? If C is greater than this dot C, then I'm going to go to the right, and I'm going to do a printout. Data is added to the right child, blah blah blah, and then I'm going to say right equals new node C, right? So if the right is null, then I'm going to create a new node and add it to the right side. On the other hand, if it's not null, then I'm going to follow the right child and pass the C along, right? So the idea is I'm going into the tree, and I'm at each, what I'm doing is I'm asking if a right child or left child is empty, and then I'm making a decision based on that. So and notice what happens, right? If C is greater than this dot C, I'm going to the right. If C is less than this dot C, I'm going to the left. If C is equal to C, nothing's going to happen, right? What do you think about that? Does that make sense? Is that a bug or a feature? It's a feature. Why is it a feature?
It's useful.
Okay, it's useful, but what a tree is fundamentally implementing is a set, right? A set. And what's the definition of a set? All the values are unique. Okay, so if I try to add something and it's already there, then I do nothing. Let that sink into your brain. This is one of the fundamental things you have to understand if you want to understand a binary tree. Make sure you get this. Okay, two-string method. So it's really hard to get a two-string method that properly represents a binary tree in any way that makes sense, but something is often better than nothing. Now this this two-string method is an override from the base node class, and what it's going to do is it's always going to put a parentheses, a left parentheses. If there's a null, it's going to put a dash. Otherwise, it's going to call left.toString. It's going to call, then it's going to put a space, the current character, a space, and then it's going to do the thing for the right. And that's, you know, a way to do it. And then I have a public string toString. It's going to create a string builder. It's going to pass the string builder to the toString method above, and then it's going to return sb.toString. I'm going to sneeze. I know I am. I can feel it. All right, any questions? Okay, so I have a height method on my class, and you might think that, hold on. You might think I don't need a height method. Actually, why do I have one there? It seems redundant. It seems like I'm just overriding the thing I built before. I have to check that. Okay, I have a method I added here called draw. And what this is going to do is this is going to format things for HTML. And again, it's going to do things recursively. And if you understand HTML, you can understand this. But the basic idea here is I have a print writer that is passed to this draw method. And each time I'm going to print something to that print writer. So I can send it to a file if I want to. I have a method called find smallest, and that's going to return a node. And what that's going to do is it's going to say, if the left is not null, then I'm going to return the left, find smallest from the left. Otherwise, I'm going to return this. Now note the casts, right? So I had a base node class, which I subclassed and added an add and a toString. And so if I want to have a find smallest, and it's going to return my subclass of base node, then I have to keep casting things, right? So because the type of left is a base node, I have to upcast it to a node before I can call find smallest, because find smallest is on the current node and not on base node. Got it? It would really make me feel good if somebody would ask a question, because I know that people have questions. Yes. Yeah, what's your name again? Lillian. Okay, so I had a base node class, which I showed you first, and it had two abstract methods on it. And what I did in this, inside this binary tree, right, I made a subclass of base node. And I have a constructor for it. And I subclass that add method, and I put like print statements in there so that if you run this code, you can see what it's doing. And then I also have the toString method, which is required, right? So the thing is, I'm going to make several different binary trees. I'm going to show you several different iterations of a binary tree, and I want to use that base node. It feels so much better. I could feel it just sitting there, ready to come out. Okay. Any other questions? Yes, Isaac? It begins with an I. Bennett? No, Isaac is, where? Yes, there you are. Bennett. Okay, sorry, Bennett. So the type of left, right? So we subclassed base. We have node is subclassing base node, right? So base node has the left and right. The left and right are of type base node, right? What I am doing in this class is I'm adding a method called find smallest. So find smallest exists on node, but it does not exist on base node. So in this method here, what I want to do is I want to call find smallest on the left node. Now I know, because it's in my tree, that it is of type node, but its type, as far as the Java compiler is concerned, is base node. So if I want to call the find smallest method, first I have to cast it to a node. Make sense? Lillian. Right. So my whole goal of finding smallest is I'm always looking to the left. Okay, so
Just a weird question, but if you want to find the smallest on the right tree, so it's basically no right.
I could call right.find smallest if I wanted to. I could find the smallest on the right tree if I did that. All right. Okay, so one of the trickiest things you can do is try to remove something from a binary tree. It's all well and good to traverse it and look for stuff and put stuff in it, but taking stuff out is a problem, right? Because if I want to take something out and it has both left and right children, then I have to do some juggling. And that gets a little bit more complicated. So let's gonna take a look at how to do that. So what I'm gonna do is I'm gonna have a method called remove, and it's going to return something of type base node. So the way this is going to work, first I'm going to say if this.c is equal to c, right? If my left and right children are both null, right? If I'm just a dangling node with no children, then I can just return a null. And if you want to remove, if you want to remove me, then remove me. I've got nothing to leave behind. I just had a sad and lonely existence with no children. Okay, on the other hand, if my left is null and I have a right, then if you remove me, then you're left with whatever I had on my right, and that's it, right? And if you remove me and my right is null, but I have a left, then you can replace me with whatever was on the left. So the idea behind the return value is I'm asking, if I remove this node from the tree, what do I replace it with? Okay, now if I have both a left and right child on my tree, then I can't just do something simple like I could in these first cases. So I could have a tree that looks like this, or a tree that looks like this. So what I'm going to do is I'm going to look at my right node and I'm going to find the smallest. Okay. That's the first thing I'm going to do is I'm going to get the smallest, and you're going to keep this picture in mind. Now, what I'm going to do is on my right node, I'm going to call remove, and I'm going to take the smallest .c. I'm going to remove the smallest thing from my right node. Okay. And so in this case, if I've got a 2, if I'm node 2, right, the thing I'm going to remove is my 3. Right. And so what I want to do is I want to take that 3 and I want to take this picture and make it into this picture, because that's how I can take 2 out and keep everything together. Right. If I take the smallest thing from the right tree and move it to the top, right, then I've got a new tree, which is still a tree, right? And I can return that from my method. Does that make sense? So fundamentally, what I'm going to want to remove, what I'm going to return is my smallest node, which is going to be this 3. But I have to rebuild the tree to look like this. So let's see how we do that. So what we're going to do is, right, we're going to remove this. We're going to remove the smallest from the right tree, and now we're going to get a right tree that has the smallest removed, and that's going to look like this, right? So when I call remove on this one, I'm going to get back a tree that looks like 4, 5, 6. Okay, and now I'm going to say the smallest dot right is equal to the remove dot right. So the smallest, which is 3, its right is now going to be the tree that it was removed from. Okay. And then the smallest dot left is going to be the original left side of the tree. Okay. And now that I've rebuilt the smallest as the top, then I can return the smallest. And that's how I remove in the more complicated case. Now I know that was sort of a drug trip, right? But it really isn't that complicated. So let's just quickly go through it again. I just want to remove, 2 wants to remove itself from the tree. So how does it do it, right? So it says, well, I'm going to replace myself, my heir, if you will, is going to be the smallest value on my right subtree. So it's going to remove the smallest value from the right subtree. And then as a result, it's going to have 4, 5, 6 on that right subtree. And now it's going to say, 3, take over my left subtree, and your new right subtree is the tree that you were removed from. You were taken from amongst the rabble and promoted to king. Okay. And then I can return smallest as my replacement. So, and then of course, if C is less than C, then I can just call left equals node left cast to node left dot remove C. If C is greater, then I can say right equals node cast or right cast to node remove C, right? So that's how we can make the remove work. Does that fit in your brain? Yes. Yeah. So the point is, right? All the complexity comes if I'm trying to remove the current node, right? If I'm not removing the current node, then I'm just doing what I always do with a tree is just passing everything to the left or the right. Right? Is it my problem or is it one of my children's problems? Right? So if this dot C is equal to C, it's my problem. I have to remove myself and return a replacement. If it's not me, then I pass it, and if it's to the left, then I pass it to my left subtree. So I'm gonna take the left, my left, which is a type base node, cast it to node, and call the remove method on my left subtree. Now that could change my left subtree, right? Because it could be the very top node of my left subtree that gets removed. So what I'm going to do is I'm going to replace my left subtree with whatever comes back from remove, because remove is always finding the replacement, right? Okay. And if and you notice that if I replace myself, right, then I return smallest. I either return null, right, left, or smallest. But if I go down these other two branches, what I return is myself unchanged, right? So if the value I'm trying to remove is not the current value, then the return value is just this, right? I don't need to replace myself because it's not my, you're not, I'm not the target of this remove. Make sense? Yes, Serene. I can't hear you. Could I show a different picture? Well, let's take a look. Let's take a look at this example again. So if I remove this node, right, all I would do is replace it with this subtree. And if I remove this node, I would just replace it with null, right? And if I remove this one, if I want to remove this one here, I would just replace it with that one. But what if I want to remove C? Well, if I want to remove C, what I'm going to do is remove D from my right subtree, right? And I'm going to take, and that's going to leave nothing. And then my left subtree for D is going to be this. And I'm going to return that. See that? So it will be DBA that gets returned. Okay. And if I return that that underscore, that space character above the C, it's just going to be replaced by the C and that whole tree, right? Okay, so let's take a look at this one. If I want to remove this one, what do? I'm going to take my right subtree and I'm going to find the minimum value. That's going to be L. So I'm going to remove that from here. And now I have this tree and that one. So I'm going to take this L, I'm going to put it at the top. I'm going to give this J to the left side of L, and I'm going to give this tree to L on the right. And then it will be removed. And then the K will be removed. Does that make sense? You get it? Yes.
I just want to make sure I understand. Basically, let's take K, for example.
Yeah.
All we're doing is we take the smallest value on the right tree.
And remove it.
We don't care about anything else, just the smallest value on the right. As long as the smallest on the right.
The smallest on the right. Because the idea is I want this whole tree to fit on the right side of the smallest node. And it will fit. If I take the smallest node out, everything legitimately can go on the right side of that tree.
Okay.
That's the reason I want the smallest. Okay. If the smallest thing could be the king of that tree. Are we loving life? Say, yes, I'm in the right major. I love binary trees. Binary trees are my spirit animal. Okay, now the other thing that I'm going to do, now you remember that when we had a linked list, we had a head and a tail. So what we need is some kind of bigger structure to hold the whole thing together. So you see that closed curly bracket there? That's the end of my definition of class node. And now what I'm going to have inside my binary tree class itself is I'm going to have a head. I need so my tree is going to manage this collection of nodes. My tree class is going to manage this collection of nodes, just like my linked list class managed its collection of nodes. But this time I don't have a head and a tail, I just have a head. And so that means I have to sort of re-implement a couple of things. So I have a height method. If my head is equal to null, my height is 0. Otherwise, it's the head height. If my head is null, my count is 0. Otherwise, it's the head count. If I want to add If the head is null, then I replace the head with a new node. Otherwise, I add to the head. Okay, and that's all there is to that. If I want to remove, what I do is if the head is null, I just return because there's, I can't remove it. On the other hand, if I want the head, if there is a head and I want to do a remove, then I have to do this wonderful thing. Does this make sense to you? Look at that. Isn't that beautiful? No, it's not beautiful. Okay, so I want to call remove. Remove is on node, it's not on base node, right? And actually, I don't need this cast. I can just say head.remove and cast the result. And let me check. Yeah, okay, the remove is returning a base node. So I do have to cast the result, but I guess I can take this one of these casts out. Hold on, where was I? Yeah, I don't need this cast because head is of type node, not base node. So I didn't need that one. It doesn't do anything. It doesn't hurt anything, but it doesn't help. All right. So, and then I have my toString, which can either return empty parentheses if the head is null, or otherwise the head.toString. So these all just pass it through, right? Now I have a draw method on here, and this is going to draw things in HTML and create a style sheet and whatnot. And then I have a contains method, which again is passing through, right? A visit, which is again passing through. And then I have a test method. And let's see what I'm doing in my test method. I create a binary tree object. I create a hash set. I create a set of characters. I go through, I take a string input. I take a string of add and removes. And what I'm going to do is I'm going to add and remove these characters. First, I'm going to add them, and then I'm going to remove them. And I'm going to check that the set and the binary tree are the same at each point. Right, well, what I'm going to check is not that they're the same at each point. I'm going to do the add for each of them, the remove for each of them. And at the end, I'm going to make sure they both have the same size. So the node count on the binary tree is equal to the set size. And then I'm going to return the binary tree. So that's how that's the test I'm doing. And then I'm adding apple and removing ape, adding avocado, removing down, adding window, removing glow, and so on. And then I have this one, which is going to draw the tree in HTML. So I think at this point we can run the code. What do you say? All right, Control A, C. Now, actually, I need to go. I have to download a bunch of things if I want to if I want to do this. So I'll just try and find where I put it on disk. What? Where did I put it? How annoying. All right. All right, so what I'm going to do, I'm going to go back to my slides, go forward. It's too small for me to see. So base node, copy link address. Binary tree. All right. Oh, okay. I put package names on these things. So I have to do this, Java minus D, classes, star.java. Now I can say Java minus CP, classes, B tree. Trees. Okay, Java minus CP, classes, trees, binary. Okay. So this creates a couple of different things. It's going to create tree.html, which is my effort to why is that not drawing? It should render. Why is it not rendering? What's going on here? Okay, there it is. Isn't that beautiful? Look at that. So I have this T at the top. To the left of it, I have an H. To the right of it, I have this U, and this U has to the left, it's got a null for empty. So I put yellow on the right and blue on the left and pink on the top. And you can sort of see that, right? And again, I get that by just recursively constructing HTML. However, I also created something called viz dot, right? So this is, remember that picture I showed you, that nice graphical one with the bubbles and the arrows? This is an input to a program that does that. And I just generate this code and I can run a script on that and generate that other nicer plot. All right. So let me just walk you through some of the things I did. So when I compiled it, because this thing has package names, if you just say java star.java, it's going to just put everything in the current directory, which is going to be difficult if you want to run the Java command. So what I did instead was I put a -d and classes. And so what that's going to do is it's going to put everything that it compiles in the classes directory. And if it's got a package name, it's going to create the appropriate directory structure under classes and put everything where it belongs. All right. That's going to make it easier for when I want to run the class. And when I want to run it, what I have to do is I have to tell Java the class path, where it should go to search for classes. And I give it that same directory that I compiled everything into. And now when I say the package name dot class name, it has the correct directory structure and it resolves things. That's what happens if you use the command line. You have to know all that stuff. Do we have any questions? All right. So we have our tests at the beginning of this thing. We have a big test where we go with all the letters in the alphabet with underscores between the words, and then that we remove nothing from that. And then we draw that tree in a couple of different ways. We also show the height of the tree on the left and the node count, or the height of the tree and the node count of the tree. We have a binary tree visitor where we visit each node of the tree and print it. We have another thing that we're going to do is we're going to say object ch, and then we're going to print the binary tree. We didn't look at an iterator yet, but there is an iterator there, so I can use an enhanced for loop. That's going to do another count of the size of the tree. And then I'm going to hopefully see the same count there. And then I can do the tree visitor for, I'm using the tree visitor to create the viz dot. And the way I do that is first I open a print writer, right? And I use this try with parentheses here to automatically close the file. I put a digraph G at the top, and then I say binary tree dot visit, and here I create an anonymous inner class of type B tree visitor. In my visit, I have my base node class, and I put down, if something is the left, I put down its arrow to the left. If something has a right, I put down its arrow to the right, and then I close the thing. Okay, so that's how I create that digraph file. Make sense? Okay, we've got 4 minutes left. 4 whole minutes.
I'm not sure you can press that you're back.
We'll see if it does. There's my iterator. And oh, look how simple it is, right? It's not so simple. So what I have to do in this case, right, is I have to keep track of state, because if I go down the left, I have to remember to go back and look at the right. So what I'm going to do is I'm going to create a stack of type base node. And I'm going to start with, I'm going to take a node as my current thing, and I'm going to iterate through it. So as long as that node is not null, I'm going to say has next is true. But my next method is going to be tricky. So first I'm going to capture my return value in object. Now, node.c is of what type? Does anyone remember? What type is the C on my node, on my base node class? No one knows. Yes, Bennett. What? It's char. Yeah, it's a character. So what happens? A character is a primitive type, right? And I'm assigning it to something of type object, which is the root class of all classes. So what Java is going to do for me is it's automatically going to autobox that char to a character, and then assign that character to the object ret. Okay. Then what I'm going to do is if this thing has a right subtree, I'm going to push that right subtree onto the stack, and then I'm going to move to the left. Okay. Now, if the left, after I've moved to the left, if that node becomes empty and the stack is not empty, then I'm going to set the node equal to stack.pop. Okay, and then I'm going to return the ret value. So all this logic is just to advance node to the next thing. And so what it's going to do is it's going to keep advancing whenever it gets to a tree. If there's a right tree, it's going to put it on the stack, and then it's going to move to the left. And if that left thing becomes null, then it's going to take things off the stack. And that's going to get it through the whole tree. So if we go back to the picture, well, let's look at this picture. So if we start with a T, right, it has a right subtree. We put that on the stack. We go to the H, right? And we can print that, right? And then, but H has a right subtree, so we put that on the stack. And then we go to E, and that has a right subtree, so we put E on the stack, and so on, right? And so I'm going to print out my left things first, and then my right things. I don't think that comes out in order that way, but it's partially ordered. All right, and that takes us to the end of class, and my battery did hold. So thank you so much.